Ayta mashhurina يودارم هم كان باشبن ومش هم كان هاتفتن إن شاء الله دسة كمان Emma, yesterday we talked about the interaction of solutes and solvents. So we said we talked about three things in the solute and solvent actually. During that time, we talked about that ionic compounds dissolve in water, especially in polars. So since it said they dissolve in water, so it means that ionic compounds dissolve in polar solvents. I think you have seen the figure or the chart that I sent you out Microsoft Teams. Then we talked about nonpolar solvents, nonpolar solutes, and nonpolar, of course, they only dissolve in nonpolar. The third part, we talked about the interaction between water and ethanol, which is alcohol. And we said water and ethanol are miscible, they can be mixed, but ethanol as a solvent is not as polar as water. It's polar, but it's not as polar as water. It has a little low polarity. And it's an intermediate between water and CCI4. There's something else. I remember that I have to remind you. I think some of you may have misunderstood the fact that what is ethanol. So ethanol, when it say intermediate polarity here, it means that ethanol has a side which acts as a nonpolar and another side which acts as a polar. So what makes ethanol a polar? The OH group, the presence of OH inside that compound makes the ethanol a polar. That's why it can bond with water. That's why it can be mixed with water. They are miscible with water. And we talked about the interaction forces between water or between polars and nonpolars. Between polars or between polar sites, the interaction is hydrogen bond. But between nonpolars, the interaction is London dispersion forces. So, for example, ethanol will bond with H2O by hydrogen bond, and the H2O will form the hydrogen bond only to the side of the polar region of the ethanol. So if you look at, for example, the thing that we drew here, we said H2O here is only facing the polar side of the ethanol and is forming hydrogen bond. It cannot face the non-polar side. That's where it will form a bond. So ethanol and polar, they get mixed, but through only one side. Another thing about the ethanol itself, throughout its own molecules, it can form both London dispersion forces and hydrogen bonds. How the polar sides of the ethanol will face each other, and the non-polar sides also will face each other. Then between the polar sides, they will form hydrogen bond. Between the non-polar sides, they form London dispersion forces. So that was yesterday's subject. So until now, what we have studied throughout the solution process, first one was the rate, second was solubility, third one was interaction. So that was three. We are done with those three. Now the fourth one, effects. So we are talking about effects. The effects, the first effect that we are going to talk about is effects of pressure on solubility. Effects of pressure on solubility. Whenever we talk about pressure, this is the fourth point of solubility. If you remember, we said solubility depends on four things. Nature of solute, nature of solvent, temperature, and the fourth one, we added the fourth one, which was pressure only for gases. That's what I want to remind you, that when we talk about only for gases, you have to know that when we talk about effects, it only affects the solubility of gases. We don't care about the solubility of liquids or solids. So if you look at the first point, changes in pressure have very little effect on the solubility of liquids or solids. The solubility of liquids or solids in liquid solvents. So we don't care about solid and liquids throughout pressure when we talk about pressure. The only thing that we talk about is gas. However, increases in pressure, increase gas solubility in liquid. So if we increase pressure of a gas, so what is this pressure that we talk about? It's actually partial pressure. Partial pressure. بس checking, بس partial pressure. What does partial pressure mean? You might remember from 11th grade in chapter 4. Partial pressure is pressure of a single gas, of an individual gas. So pressure of single gas, for only one gas, the gas itself. Because we have total pressure, which was the pressure between the different gases all together. For example, the air that we live in, the air is a total pressure between nitrogen, oxygen, hydrogen, CO2, and all of them. But if you take pressure of CO2, it has a very low pressure inside the air. Why? Because the amount is very little. So when we talk about here, we are talking about pressure, we mean partial pressure of a gas. And if we increase pressure of a gas, we can increase solubility of that gas in liquids. We don't need gas in gas. Because gas in gas, they don't need pressure. They just diffuse into each other. They form diffusion. They don't need to be dissolved. But for liquids, there must be a high amount of pressure for the gas to be dissolved. For example, if you have a soda, if you have a soft beverage, how can you dissolve some gases when you drink it? It has been added by pressure, and it's directly proportional with the solubility. So the higher the pressure, the higher the solubility, the more the solubility of the gas. If you increase the partial pressure of that gas, the higher the solubility will have. So if you look at the next point, as the amount of dissolved gas increases, some molecules begin to escape and re-enter the gas phase. So when we put gas actually into a solvent, some molecules, just like the solid, some molecules were at first trying to become solid again, but then they dissolve. But the gas is a little bit different. So when we start putting gas into a liquid, most of the gas will enter the liquid, but gradually some of them will come out as well. An equilibrium is eventually established until it reaches what? Until it reaches equilibrium. It reaches equilibrium between the rates at which a gas molecules enter and leave the liquid phase. So if I draw a figure for you, let's say this is a bottle of soda or Pepsi or anything like that. For example, this is Pepsi or Coca-Cola, anything of those kinds. And some gas and the pressure has been added to this bottle, and the cap is closed. The cap is closed. Let's say the liquid is here. Until this point, there is the liquid. Until here is the liquid. For that liquid, when we put the gas, some gas solution, some gas will be dissolved, so this part will become a solution. Some of them will become solution. The gas particles are dissolved inside the liquid here. The gas particles are dissolved here inside the liquid. But there are still some gas particles trapped here, like this. Gas particles are trapped here. These gas particles, when they apply pressure on this surface, of the liquid, they form an equilibrium. So after a while, when we leave them, when we put a lot of pressure into these cans, into these bottles, and we close the lid, and we leave them, they eventually reach equilibrium. What is that equilibrium? The gas trapped here in this space, the gas trapped here in this space, will apply a pressure on the surface of the liquid forming the equilibrium like this. Some gas particles will try to enter the liquid, and at the same time, some gas particles are trying to come out. So there is two processes. Dissolution, so it's not like precipitation. We said it's dissolution and precipitation. It's the same thing, but different words. Dissolution, it was for the saturated, for the solid in liquid, dissolution and crystallization. But for this one, it's dissolution and gas escape. Dissolution, so this time, when the gas and the solvent together, when they get mixed, they become solution. But the solution of gases, of course, it must be in a closed system. It must be in a closed system. They are always in equilibrium. So this means a reversible reaction. So they can go to the forward, they can come backwards again. They can get reversed also. The forward reaction is again dissolution. Dissolution. The reverse is gas escape. Gas escape. So at that point, the amount of gas entering the solution is equal to the amount of gas coming out of the solution. That's why when you open the bottle like at once, all the gases in this space will escape, and only the gas inside the liquid will remain. All right? We understood that. Now we close the lid again. We close the lid again. When you close the lid, the gas has been lost in the space. لو بشي أعلى غازك ونبوا غاز تاني ما بو لبرتو كرتوا غازك الري. Now the gas was lost inside this space. So what does it do? What does the solution do? It will try to reach equilibrium again. It will try to reach equilibrium again. How? So we don't have this part, let's say. On again. When you open the lid, when you open the cap, there is no gas here. Gas is not left. So some solution, the gas from the solution will try to escape upwards again so that it can feel the loss of those gases. Until when? Until more gases are present inside the space and the same amount of gas re-enters the solution. But what has happened? Now there is less gas inside the solution. Essentially, gas can the solution. The next time you open the bottle and drink the soda or the Coca-Cola, it doesn't taste the same as it was before. أجاب كردية ساشرح كيف كمان لما كاتب بطل ساردي مانها لسري سرو بهو بريشري زورو كتكرا أو برجاز دامن أمانته أو جاز اللي قلبك في دكايا باب المكوي إريها لقلبك في دكايا لا حالتك إكوليبريم معه شون أو جازي كده ناو بابل بوشاكا ده هو مجموعة شيء هولا بيت تناو بطلقه مجموعة شيء هولا بيت الدرا هولا بيت ناو مزه هولا بيت الدرا لم بينها كبابل أمر رؤيات هو بابل ساعدك هلا بشر أو جازي كده ناو بوشاكا أو يتدرا أو غازي تيانا ما طبعا غازك غاز أو غازي هر هواء عتالينيا غازي CO2 برجيك زور CO2 تكرا بس كتو إكيتو رجي هواء CO2 زورنيا CO2 كي تدرا كسيوتو كهات درو انجا تداخلو انجا ران بوشاكا او سيوتو تيانما دوباره بطلقه دسكاتو بدرس كنوي سيوتو كاتو ناو بوشايكا كاتو ناو بوشايكا شي روايات برلا غاز كيك ناو لكده كاتو ابو استا هاتو تدرو بو بغاز كي جواز ولا بطلقه هاتو درو انجا دوباره غاتو بكلوبريم انجا ران ناس نكا غازي كبت. Now the thing that I explained before, if I write it down according to this rule, we have in 11th grade we have a principle called Le Chatter's principle. What is this Le Chatter's principle? Le Chatter's principle means, even though we are in the book, it's not mentioned as Le Chatter's principle. It will be mentioned in chapter 7, but since it was explained in 11th grade, that's why I have written it here. But let me give you the definition. Le Chatter's principle means when a system at equilibrium will face a change or a stress is applied on that equilibrium, it tries to change. It wants to relieve the stress to a direction so that it can reach equilibrium again. Again, Le Chatelier's principle. If a stress is applied on an equilibrium system, the direction of change will be towards a direction to relieve the stress. What does that mean? Let me write this equation according to CO2. So now we have CO2 with water, let's say. With water. They become a solution. The solution is the soda. When it reaches equilibrium, when the cap is closed, this side is the solution. This side is escape, gas escape. Right? This side is gas escape. Now, Le Chatelier's principle says if we remove something or something is decreased, I always do this form or this thing. For example, imagine, for Le Chatelier's principle, so that you can understand, imagine you have a room or a place where there is soil and all the soil is flat, like this. Let's say the soil is flat, like this. And we say the soil is at equilibrium. Now, for example, after one to a couple of days, a lorry or a carrier will bring more soil to this location, to this container. And they pour let's say this is equilibrium, they pour the soil on top of one side. So here's the soil. Now one side has more soil than the other side. So what do we have to do? What will we tell the workers? What do they have to do? They have to shift this amount. They have to shift this amount, the extra amount, to the other side. Why? Because it has to be level again. It has to be at equilibrium again. أبد شيء كله تجاري كتير ريك بيتو ببدو equilibrium. بلام كواتا شفتك برشلة أقري برو لاكيتر كواتا هر كاتي equilibrium لا يكزور بو أبي هو بابشي بوشلاك أبي برو بلاكيتر بويها نختي كبا بلاكيتر بالرياكشن كشبه وكشون أمري أقول لك نختي كمان بلاكيتر بوشي لبت so that it can relieve the stress. Some part of it has gone to the right side. We move it to the right side. But imagine, what if instead of adding some solute, a customer comes and some solute is removed like this. Some soil, sorry, not solute, some soil is removed like this. So there is a lack of soil here. Again, what would you tell the workers to do to reach equilibrium again? Now this time, you have to take soil from the right side to the left side. So the shifting, you bring more soil from the right to the left. Why? So that you reach equilibrium again. We begin to equilibrium. Same thing is happening here. If we said, if we increase pressure of the gas, the solution or solubility of the gas increases. What does it mean? It means that we can dissolve more gas. Look at this reaction. We only have CO2 as the gas. If we increase pressure of this gas, the CO2, وەکو ئەوی گڵەکە کە لێرە زۆر زیای بوو بەرز بۆچی لێ هات شفتمان بۆ کرد بۆ کوێ ئەگەر بۆ منە بەرز بوایەتەوە ئاوا شفتمانە کرد بۆ لای ڕاست. Now, when CO2 is increased, the shifting is to the right. ئەبێ چی لێ برێ بەرەو لای ڕاست بڕوا. ئەبێ بەرەو لای ڕاست بڕوا. بۆ بۆی زیاتر بچێتەوە. So that it can dissolve more because we have more CO2 and it will like distribute some of the CO2 to the other side as well. To restore equilibrium again. Equilibrium. But if, so I'm gonna draw this one in green, if CO2 is decreased, what will be the direction of the shift? the left. How is that possible? For example, when you open the cap, you are removing CO2, you are decreasing CO2, decreasing the pressure of CO2. Now the shift will be to the left. What is to the left? Forming CO2 again, and solution, of course, when it comes to the left, it's coming to the left on the count of what؟ لصح حسابي شيء ولا شيء. هيك شيء دركاته. لصح حسابي solution on the count of solution. So the solution will decrease. Why? Because we are removing CO2. Some of the solution must go back, form some more CO2 again and water again. أبي بقرأته بدوها شيء كاتو نختي آية تردوس كاتو لغا CO2. شكبوا CO2 كلا برا. So that's the effect of pressure. If we increase pressure, more gas will be dissolved. So solubility will increase. But if we remove the CO2, if we decrease the gas pressure, solubility will also decrease. So the whole thing is actually here. That is this point. This is the point. شباب فواتا بفيل شاتلس برنسبل هر كاتك لا يكبرز بوا يعني ما كبروا بفيل شاتلس برنسبل هر كاتك لا يكبرز بوا شفتك بو لا كترة هر كاتك لا يجنزم بوا شفتك برو خويتي يعني برو أولاد بوننا CO2 ما ذاكر شو برو لا كترة أعطيه سولوشن ذاكر CO2 من كم كردو شفتك برو خوي هاتو بو يجيب بيتو بو أويك خسار بو أويك روشتو compensate كاتو درز بيتو. All right. Any questions here? Unclear.
Sir,
Yeah.
we have a maximum amount of the solution that can be dissolved in a solution.
Yes.
Or do we have like this thing, like this amount for gases
Actually,
in
no.
liquids?
For CO2, good question. For CO2 in liquid, actually no, because that's a good question. Because the more we put pressure, the more we can dissolve the gas into the liquid. Yes, after a while, we cannot dissolve as much as before. It will decrease. It has to reach a limit. But reaching that limit, that saturation in gases is different. In gases, it's depending on the pressure, that amount, the maximum amount. We don't have a maximum that we can say it cannot like it will reach saturation at that amount. No, for gases, it's totally dependent on pressure. At some certain pressure, it will only take some amount, and we call it saturation. In another pressure, we take, like, for example, for solids, we'll talk about it in solids, in liquids, it's dependent on temperature. If you increase temperature, more solid can dissolve. Increase more solid can dissolve. It will reach a point where, like, by increasing temperature, you can always dissolve some more. The same thing for gases. If you increase pressure, you can dissolve more. Increase pressure, you can dissolve more. All right?
Basta.
Vale.
Gazaka la liquidaka dissolve non la bipsiaka. liquidaka زياكا وا
اگر گازەکە لە باڵین کەم بکەینەوە
لا گازەکە کەتیەکەی خۆی لیکویدەکە ئەگەر لە ئاستێکا بێ زیاترە بێ
خۆی گاز لەبەرەوەی پارتێکڵەکانی زۆر بچووکە زۆر وردە عادەتەن ئەوەنە ئەفێت ناکاتە سەر سایزی ڤۆلیۆمەکە ئاین سەر ڤۆلیۆمەکە ڕەنگە ڤۆلیۆم ئەوەنە نەگۆڕێ
ئەگەر ئەوە بیپسیەک گازەکە هێن بڕۆ لیکویدەکەی کەم ناکە
ئەگەر کەمیشکە زۆر کەم فەرقەکە چونکە پاناڵم پارتیکڵی گاز ئەوەنە بچووکە ئەچێتە بینی مۆلیکۆڵەکانی لیکویدەکەەوە تیاوونە بێت ئەوەنە فەرق ناکات بەس هەرچۆنێک بێ بەڵێ ئەبێ کەم کات چونکە هەر ماسی هەیە هەرینی خۆی هەیە بەڵێ ئەبێ کەم کات بەڵام ڕێژەکەی زۆر کاتە لێرە مۆزوعەکە چی بوو هەتاکو پرێشەر زیاد بکەین گاز زیاترێتێتەوە پرێشەر کەم بکەین گاز کەمترێتێتەوە What if, so we talked about partial pressure. So when we want to dissolve CO2, the pressure of CO2 must be increased. All right, not the total pressure. What does that mean? It means that, for example, if you put another gas in order to increase the total pressure, let's say an inert gas. What does inert gas mean? A gas that's not in the container and that we don't use it, and other than the given gas. For example, doesn't affect the solidity of the given gas. Adding helium has no effect on CO2. For example, if you want to dissolve CO2 and you add some more helium to increase the pressure, helium cannot increase the pressure of CO2. That's why it will not affect the solubility of CO2. It doesn't either decrease it or increase it. كواتا جابته إما غازك تر لغير أو غازك همانا بتوانينو لأنه طولش نكا بونونا إما ما نسيو تبتوانينو أجر بيتو هيليوم بتوانيتو لأنه هيش مهمية هيش تأثيري هيتياناكا هيش أفكتي شينية مثلا هيليوم بيت بوشي لينا نكتبك أبونا باسي هيليومكات هيليوم مثلا نوبل غازا نوبل غازا كان كنت اكيد يمكن الرياكشن معك وكتبك دائما مثلا او شيء نمونيه helium, neon, xenon are always talked about. Why? Because noble gases are not reactive. They don't react with the gas. For example, if it says oxygen, a student might ask, well, the oxygen might react with the CO2, and that's probably will happen. But if we say noble gases, we are certain, we are sure that none of the noble gases will react with the CO2. And it doesn't have any effect on the solubility of CO2. And we call those extra gases as inert gas. Inert gas. All right. We are still on the solubility of gases. What do we call this law? What do we call this phenomenon? This thing about gases in liquids? We call it Henry's law. This is important. What is it? What is Henry's law? Henry's law states that the thing that we wrote here, this rule, this is Henry's law. Look at this explanation, or look at this part, and look at the definition of Henry's law. Henry's law states that the solubility of gas, yes, that is solubility of gas, in a liquid is directly proportional, yes, this is directly proportional, to the partial pressure of that gas, yes, on the surface of that. So this explanation and Henry's law are the same thing. They have the same definition. كاتب كيما لسه باس معك solubility gas directly proportional لقال partial pressure gas كيا أو تشيا أو PO3 Henry's law PO3 Henry's law رنجا بسيابته بلا relation لبيني if in a question asked what is the relation between solubility of gas and like partial pressure is called, you will say Henry's law. All right, let's continue.
Teacher,
Yes.
what is the difference between the Chatelier's principle and the Henry's law?
Henry's law talks about the relation. Le Chatelier's principle talks about every type of equilibrium. Henry's law only talks about relation between gas and partial pressure. All right, gas
Okay.
and partial pressure. Le Chatelier's principle talks about every single type of equilibrium. Le Chatelier's principle talks about if we change an equilibrium, what happens. All right, so that is the difference. Now, in carbonated beverages, the solubility of carbon dioxide is increased by increasing the pressure. So in carbonated beverages, like the things that we drink, if they want to dissolve CO2, they have to increase the pressure. The seal containers, sealed closed, contain CO2 at high pressure. Look at that pressure, 5 to 10 atm. So the air, the whole thing, nitrogen, oxygen, CO2, everything that we have in air, it's almost 1 atm. يعني همو غاز كان. إمتى أجي هر همو بيكو أنجا كاتيك atm. أنا لا فلسطينية ناجداتي atm. ليه كم تيشا. But so the air we live is 1 atm. But for bottles like this, for drinks like this, only the pressure of CO2, not the total, only the pressure of CO2 which is added to the bottle is around 5 to 10 atm. يعني بس CO2 كبتاخ تانية كنت بدأ atm. which keeps the CO2 dissolved in the beverage. Why? Because at higher pressure, more CO2 will be dissolved. When the beverage container is opened, now we open the container, we set the pressure above the solution is reduced, the pressure is escaping, and if you still leave the container open, or for example, if you leave the container, the cap open, after 1 or 2 hours, if you drink the soda, if you drink the beverage, you can see there is no gas left. All the gas has escaped. What do we call that escape? Because the CO2 is constantly decreasing. That's why all the gas is escaping. That escape, that rapid escape of gas from the liquid is called effervescence. 1 year, this question, this definition was asked. So like a definition had to be. What is the rapid escape of gas from liquid? We'll say effervescence. So I wrote a definition or an explanation on top. We said escaping gas is one direction. From now on, instead of saying gas escape, here's how we're going to do. Gas with solvent, liquid solvent, like this. Please write this down. Solution. All right. On this side is the solution. On the reverse side is effervescence. Instead of crystallization for gases, it's effervescence. What is effervescence? The rapid escape of gas from a liquid. فأعتقد كتب الطاقة دوای ساعت 2 ساعت سیرکی غازیانه ما بۆ لەبەری هەموو گازەکە هاتۆتە دەرەوە کە پرێشەری گازەکە کەم بۆتەوە بۆ هاتنە دەرەوە خێرایە پێوترێ چی؟ effervescence. All right. We have a ministry exam question. The solubility of gas in liquid would be increased by an addition of electrolyte. No, it doesn't have anything to do with emulsifier. No. Agitating, definitely not. Agitating is actually the reverse. If you agitate it, some of the gas will escape, I think. Increase in its partial pressure. So yes, if you increase partial pressure, solubility of gas will increase. All right. Do you have any questions?
Sir.
Yeah.
What was the emulsifier thing in written answer?
Emulsifier is the emulsifying agent in section 1. We talked about colloids.
Oh, okay.
حەزە نەمەتوانی اونجا یەکجێتی خاڵەکانم بۆ دووبارەکەیت و حەزت نەبێت
هەمووی بە ئام باسکەمەوە یان بە خاڵ لەگەدا بڕمەوە
بەس ئەم خاڵانەی خوارەوە این کاربۆنێت بێڤڕێجس
کاربۆنێتی بێڤرج یعنی ئەوەی کە بنە ساردیشتەکانە توانەوەی کاربۆن دایۆکساید بەچی زیادکرێ ئەگەر بێت و پرێشەری گازەکە زیادکەن واتە CO2 بە زیادکرێ لە معمەلەکانە ئەچن بە چەندێک بە چ پرێشەرێک گازەکە زیادکەم خانە چەندێک پرێشەرەکە نزیکی 5 بۆ 10 ئەیتیام یعنی 5 بۆ 10 ئەیتیام بەس پرێشەری CO2 نەکو پرێشەری هەواکەش ئەسامە مەسەن پرێشەری هەوای خۆمان 1 ئەیتیامە بەهەر هەموو گازەکانەوە بە تۆتاڵ ئەکات 1 ئەیتیام ینی بە نایترۆجین ئۆکسیژینەوە ئەو بەس CO2 5 بۆ 10 ئەیتیامە بێت بۆیە کە کاتێک طبعاً ئەمە وای لێکردن بتوێتەوە بۆیە کە کاتێک بە پڵەکەکەینەوە پرێشەری CO2 ئەوە لە پۆلی یامەسەن 11 خەنوتانە پرێشەر دامن لە های پرێشەر و بەرەو لۆ پرێشەرە بۆ منە با چۆن هەڵەکات لە های پرێشەر و بەرەو لۆ پرێشەرە باشە کەواتە کاتێک ئێمە بتڵەکەکەینەوە ئەو پرێشەرە زۆری کە لەناو بتڵەکەیە بە یەک سەپەرەکرێتە ناو پرێشەرێکی کەمەوە کە هەوایە پرێشەری CO2 زۆر کەمە ئەویش حساب پرێشەری CO2 کاکات لەبەر پرێشەری CO2 ئەوە نەکەمە لە هەوای یەکسەریەتە دەرەوە بەرەو پرێشەرە کەمەکە ئەڕوا وای لێ پرێشەر و گاز لەناو کۆنتێنەرەکان نامێنێ ئەگەر تۆ ئەو بتڵە بەکراوی هەر بەجێ بهێڵیت باشە کاڵێ ئەها بەکراوی بەجێ بهێڵیت پرێشە کەمی کردو بۆیە CO2 هەر ڕوا هەرێتە دەرەوە ئەم ڕاکردنە خێرایش ئەم هاتنە دەرەوە خێرایش لە لیکوید لەلایەن گازەوە پێی ئەوترێ ئەفەربەس
مامۆستا
بەڵێ.
یعنی ئەم گازی کە تێکراوە لە شەریکەکە بە پرێژەری ئەوە تێکراوە کاتە دەبەکەوە کە لە معمەلەکە تێکرا ینی ئەمە زەختەکەی کە تیان کردو پێشتر
بەڵێ ئەمە مەلەکە پێشەرێکی زۆر ئەکرێتە ناو بڵەکەوە یەکسەر سەرەکەشی داخن بۆ ئەوەی ئەو بۆ پرێشەرە زۆرە بمێنێتەوە جەدامە لە چی شای لە ئیکولیبرمە لەناو خۆیان گازەکە ئەتوێتەوە یەتە دەرەوە ئەتوێتەوە یەتە دەرەوە تێگەشتی باڵە
ینی هەنێ جا زۆر ڕایوەشێنی بێ بە عرزاتەقێت لەبەرەوەی پرێژەرەکەی
ئەوەی
زۆر
خێڕاوشێنی هۆکارەکە چییە لەبەری پرێشەرەکەی زۆرە ئەو گازی کە لە سەرەوە ماوەتەوە بۆ شایەکە کە ڕایوەشێنی ئەچێتە بەشی ژێرەوەی لیکویدەکە تۆ چی تێکەی گازەکەی کەهێتە ژێرەوە ناشتێتەوە کە نابێتەوە تۆ خۆی گەشتە ئیکولیبرە ئەیخیتە ژێرەوە لە ژێرەوە کە ئەوێ بێتەوە دەرەوە بۆ سەرەوە تۆ لەگە خەڵی ئەبچڕیت یەکسە پا بە لیکویدەکەەوە ئەوە بێتەوە دەرەوە بێتە بەرەو سەرەوە بێتەوە بەڵام لەژێر لیکویدەکە ئاسی بووە یەکسەر لیکویدەکەش لەگە خۆیان هێنێتە سەرەوە بەڵام ئەگەر بۆ منە ڕای بۆشێنی وازیشیت وای لە وازی لەبێنی دوای دەداقی ئەکسێرکی ئەتیادی بۆتەوە هاتۆ تۆ سەرەوە لیکویدەکە چۆتەوە ژێرەوە بەزەگەر یەکسەر بکێتەوە ئەو هۆکارەکەێتی لەبەری پرێشەرەکەی زۆر زۆرە ئەچێتە ژێر لیکویدەکە یەکسەر لیکویدەکەش لەگە خۆیان هەڵە
ناوسا بەڵام ئەتوانین بیتەقینی هەر بەگە ڕایوە شەقینی بی بە عرزانەی کردێکس ئاتەقێت
ئاخر ئەوە چیەکە ئەوە تۆ ڕایەوە شوێنیت ئەی بە عەرزە دووبارە هینێکی کەمەکەیتەوە ڤۆلیۆمەکەی کەمەکەیتەوە مەجای کە بکەیت ئەوەیە پرێشەر خۆی ڕاستیە کە ئەتەقێ بە پرێشەرەکەی بە ڕاوشانەکە جاریان ناتەقێ ئەو بە ڕاوشانەکە نییە ئەوە بە زەختی کە ئەی بە عەرزەکە ئەتەقێ یەک دەبەکە زەعیفەکەی دوو کە ئەیکێشی بە عەرزە زۆر بێجار ئەوە بەشێک تۆ نایبینیت ڤۆلیۆمەکە بچوو کردوێتەوە لە پۆ یانزایمە خوێنومانە کە ڤۆلیۆم چووگەبێتەوە چی زیاکات پرێشەر زیاد کردووە بە ڕاوشانم پرێشەر زیان ناکە بە کاکێشانەکە پرێشەرەکە زیاکە کە پرێشەکە بۆ ئیمپاکتە پرێشەرەکە زیاکە کە پرێشەکە خۆی زۆر زۆرە ئەوەی تر زیاکەی بڵەکە تەحملی ناکە تەحملی ئەو پرێشەر زۆر ناکە بڵەکات
تێگەشتم بەس خۆش بێت
take a rest for 10 minutes. When we come back, we'll talk about the effects of temperature and solidity, which is an easy subject.
How is solubility of gas is proportional to partial pressure? عزنا بيويك بس العيبة مسكت والله مين لنا بوم.
سيرجع بابا. Solidity gas دائما directly proportional لقى partial pressure. يعني شيء يعني أجر بيتو. كلام partial pressure يعني pressure الجاز لقى بتاعك ثانية خوي. باشا. أجر بيتو أو pressure زيادكن يعني جازك خوي pressure زيادكن إما أتواني رجي كي زيادتر ها solubility شيء. ڕێژەکەی کە ئیتوێنینەوە کەواتە بە زیادکردنی پرێشەری گازەکە خۆی بۆ نۆکو ساردەکە گەربانی گازی زیاتر بتوێنینەوە ئەبێ پرێشەرێکی زۆری تێ بکەین ئەوەی ئەنچیمان کردو پاشە پرێشمان زیاد کردووە بۆچی ئەو پرێشەرە زیادکەن بۆی سۆڵبڵتی گازەکە لە ناو لیکویدەکەیە زیادکە باشە بۆی گازەکە زیاتر بکرێتەوە ئەوە ڕیلەشن لە بینە دوانە جا هەتاکو پرێشەرەکە زیاتر بێ سۆڵبڵتەکەش زیاتر بۆیە ڕیلەشنەکە چییە خۆش راحتي ورقنو الله يعطيك Now we continue on the effects again. So we have two effects, two changes. First one was pressure. Second is temperature. But for temperature, we can talk about both of them, like even gases and also liquid and solids. First, when I talk about effects of temperature, I have divided the subject into two parts. First, effect of temperature on solubility of gases, on solubility of gases. So increasing temperature decrease solubility of gas solubility. Why? Again, if you remember, I told you, whenever we talk about increasing temperature, we have to think about kinetic energy. As the temperature increases, the average kinetic energy of the molecules in the solution increases. Kinetic energy increases. So again, kinetic energy equals to 1/2 mv squared. V will be speed or velocity. A greater number. So what happens if the kinetic energy will increase, or if it increases? A greater number of solute molecules are able to escape the attraction of solvent molecules and return to the gas phase. So what does this mean? It means that I think it was the same thing for rate of dissolution. I explained the same thing. Every time we increase temperature, every time there is kinetic energy, the attraction between solute and solvent will be less. For example, picture like this, imagine like this. Four people, four kids, are all of them are holding hands. They are walking. One of them will have a very high energy and it starts to move very fast. It starts to run very fast and have a lot of energy. At that point, he cannot, or that kid cannot hold hands with the other kids. Why? Because imagine three of them are walking slowly. Fourth one is moving very, very fast. So at that point, the attraction, the bond between the three kids and that kid will be broken. Same thing is happening here. When the kinetic energy of gases are normally high, and if you increase temperature, you are increasing kinetic energy of the gases a lot more. At that point, the gas particles cannot form a attraction force, cannot form a bond with the liquid that is dissolved in. And this attraction force is broken between the liquid and the gas. Broken between the liquid and the gas. That's why the solubility of gas is inversely proportional with temperature. لەگەڵ gas و هین temperature بابلين عكسي يكن. For example, imagine this. When you leave a beverage, like a carbonated beverage, all right, a soda, open, but one of them in the fridge in a cold place where temperature is low, one of them outside where the temperature is high. Which one do you expect to be for the gas to remain more than the other one? For example, if you want to drink the beverage inside the fridge after 1 hour and drink the beverage outside of the fridge after 1 hour, you can see that less gas has escaped in the one that was in the fridge, the one that was cold with the low temperature. Less gas has escaped, more solubility is present. But the one outside, since it's hot, it has a higher temperature, the gas particles have escaped a lot more. So solubility of the gas has decreased. فأعتقد بيت بونونا دو كونتينر من هذيك سودان تبي كان سلاجك هذا أبدي كان الدرو عندنا. أو هنا سلاجك لبرو السابع لبرو تمشاركي كمان. solubility كشي باشترا. gas كان زورنا كده. بس إذا جرم بيت الدروية تيجي في ساعات يخوي تو تاني يجناش. كان يوفري أوكا كان شر. gas كان ما هو لبرو اللي شو يجرم ترى gas solubility كان. temperature برز بتو solubility كم بتو. كsolubility كم بوي يعني زيادة escape. كsolubility كم بوي يعني زيادة escape. So when you're living in the hot place or in the warm place, temperature has increased and the gas particles run, or the gas particles escape the liquid more rapidly and the solubility will decrease. That's why gas solubility is inversely proportional with temperature. Inversely proportional. If you increase temperature, gas solubility will increase, and vice versa, of course. So it might ask a question: in which one of the following gas escapes more? You will say at high temperature. At high temperatures. So look at this graph here. This is actually solubility of gas. I think on like depending on temperature. So an example here is SO2. An example here is SO2. SO2. Look at as temperatures increasing, the solubility of gas is decreasing, like this. This is solubility of gas is decreasing towards below. Now, from when it's 0 Celsius here, solubility of SO2 is 80 milliliters can be dissolved. 80 milliliters can be dissolved at 0 Celsius in water, of course. What about below 0? Why there isn't below 0? وش اللي خاص فروني أجا كسر بخالله؟
ما صلبري بس ده.
لبري بس ده. تقول لنا سهولة شيء توين. تقول gas نتواني بيت أنا سهولة. عشان بلام. But you can dissolve gas in liquid. So from 0 and above, it is liquid. Now, it's 80 Celsius. 80 milliliters here at 0 Celsius. But when temperature is increasing towards the right, solubility is decreasing. Same thing for these gases as well. As temperature is increasing, solubility of these gases are decreasing. For the oxygen, the amount is so small, the solution of oxygen is so small, that's why you cannot see the change clearly on the scale. But if you pay attention very, very closely, there's a slight change. See, it starts from here. Look at it's going down by increasing temperature. توصل بأكسجين لبري كامل توتوس لسه أمس كيلا جوان درناكه لتشاو كيا لتشاو H2S و CO2 شون كتيا هسا كسكالة كي أكسجين بالتاخت نبينين جواز له بو أجا بقرن السر figure what is the scale of oxygen? Look at the figure above here. See, CO2 is dissolving more than oxygen. See, oxygen is very, very little. It's like 0.2 or then like around 7. And as temperature is increasing, temperature is increasing, the solubility of oxygen gas is decreasing. And we're doing the ring of oxygen gas CO2 gas is decreasing from 0.335 towards 0.058 as temperature increases. Right? Now, let's continue with our subject. Now we talked about gases. What about solids in liquids? All right, solids in liquids. Generally, effect of temperature on solids and liquids can be determined easily. Why? Because they are all different. Some of them will be affected more, some of them will be affected less. Some of them will decrease because it affects directly some very much and little on some. While sometimes solubility of solid decreases with an increase in temperature. بوي مناتو أني يكسر جاري كدني كتطور جاري كده. باشا. أيشون يعني أبي بعم بكompound سيري كده. But generally it will increase. You can write. I think I have written it somewhere down here. You can write it down. Generally, or you can just edit it. Generally, solubility يعني بعم زيادة increases. So generally, solubility increases. For example, KNO3, solubility of KNO3 increases a lot. Look at this figure. This is KNO3. This is solubility at 0 Celsius. After that, when temperatures increase, look at this solubility, how the solubility is increasing. In 100 Celsius, 0 Celsius, I think it's around like 17 or something. But, or like 14, I think, yes, 14. But in around 100, reached 240 above. هيك لا 0 سلسيوس لخوار بيستوي ل 100 سلسيوس أولا أتوتو نزيدي 200 شلو برسالة او وانا قرا كبس راح طالما هي تما هي بورادين نقرا even lithium sulfate has decreased so and generally they will increase but lithium sulfate only this one written specifically in the book. What is the name of this one? Cerium sulfate. These ones decrease solubility by increasing temperature. But mean temperature هنا كان زيادة. ضمن السير كمان كان solubility. نايلين cerium sulfate. جيد دونو على رب بقولنا سدونو سامبون نسم. حتى أنا قبل بشكل نسم. على رزق إذا نتعامل أمس بنسم. ليثيوم كربونات. أمالك شو درم هنا ليثيوم كربونات؟ لا table from the table. See, lithium carbonate 1.54 at 0 Celsius, 1.53 at 20 Celsius, and it's decreasing until it reaches 100 Celsius. So lithium carbonate also decreases solubility as temperature is increasing. أتاكو مثلا temperature زيادة seeking solubility كما كان. لو أتبع إما أمانة معنى. أو السدانين ذكا ليثيوم صلفيت أكش من هذا لم جرافوه هنا كاتب ليثيوم صلفيت cerium sulfate and lithium carbonate. ماشي lithium عملنا أوكي. Lithium carbonate. These three decrease their solubility as temperature increases. Why some of them decrease? Why some of them increase? Generally, it's connected to this point. It's related to this thing. Even though this part is not actually mentioned in the book, that's why I haven't written it in the booklet, and I'm going to write it down for you in a different way. We will say for endothermic solution, which I'm going to talk about what is endothermic solution. If temperature increases, this sign means increase. If temperature increases, what happens? The solution increase, then crystallization decrease. These always must be opposite of them. But and of course vice versa. If temperature decrease, the solution decrease, crystallization increase. Like that. But for exothermic, if temperature increase, the solution decrease, crystallization increase. Vice versa, if temperature decreases, the solution increase, crystallization decreases. طبعا بهو شيء بهو اندوثيرميك واكسوثيرميك وا اگر اندوثيرميك بو بشو ازاله اگر اكسوثيرميك بو بشو ازاله اگر تو بس تنها مثلا زیاد کردی تمپریچر تبدید باقی تو خود تو ان اکسیدیت يعني بس زیاد کردی تمپریچر که لبر if you just memorize the increasing temperature for the different solutions you understand you can find the other one for decreasing temperature as well. All right, we will leave this note here until we understand something else. So that was the effect of temperature on solubility of solids and in liquids. All right, any questions? بس بسالي يلا بقى.
صعب زغير هل مين تو بوي فريا كاين بينوسين واخيرك عزلنا.
بس.
مامۆستا دیدێک تەمپێرچەری زۆر بێ گازەکە تیا دیسۆڵڤە بێ
بەپی ئەو کاتە ئەبێ بکەنە سەر پرێشەرەکە پرێشەرەکی چەندێکە ئەگە پرێشەرەکی زۆر بێ ئەتوانین بەرامبەر هینەکە بۆستینەوە بەرامبەر ئەو تەمپێچەرە بۆستینەوە لەو کاتە مەسەلەن هین بێت بتوانین بیتوێنینەوە بەس دەگەر پرێشەرەکی زۆر کەم بێ ڕەنگە هیچ ناکرێتەوە تاوا بگەن
دەست خۆش بێت.
Now we talk about enthalpies of solution. What is enthalpies of solution? Enthalpy means change in heat. Change in heat. Internal heat. Change in heat. When we dissolve something, when it says change in heat or enthalpy, when we dissolve something, what happens to the heat? What happens to the energy change in the solution without us doing anything? It's just what happens when we dissolve itself and what happens to itself. For example, when we say enthalpy of solution, the formation of a solution is accompanied with energy change. Energy will change there. For example, by changing potassium iodide, it's better to memorize these two. By changing potassium iodide in water, the outside of the container feels cold to touch. مثلا قال كي أبتونينو potassium iodide لنا أوا كدرسي لهناك skin feels cold to touch. ساردة. Dissolving some sodium hydroxide in the same way, the outside of the container feels hot. طالما قال NaOH بتونينو هو شر عين compound. It feels hot. So what is happening here? When it feels hot, it means that temperature is increased. When it feels cold, it means that the temperature during the solution is decreased. Change the temperature. It will form these hot and cold solutions. We are not talking about effects. We are talking about the change that will happen during the solution. In the Ki, the formation of solid can either absorb energy. So when we dissolve a solid in liquid, it can dissolve, sometimes it will absorb energy. Like what? Like Ki. So if it absorbs energy, it will feel cold to touch. Connect يعني كوبيكو. كواتا أجر energy absorb كا كذا سيلين هستكن شيء ساروا. Or formation of solid liquid solution can either release energy. Like what? Like NaOH in water. So if it releases energy, it means that it feels hot. كواتا أجر بعم energy absorb كرت سهرده. أجر release كرت إما حسب جنيه. اگر ابزورب که ساروی این تمپرچرکی داوزیو اگر ریلیزی که این تمپرچرکی برز کرده سولوشن که برز کرده اما دستگاه تمپرچر من نکرده او پیشتر بس یو معنی کرد اگر اما تمپرچر برز کنم. Alright. Before dissolving begins, some solid particles are held together by intermolecular forces. نتیجه یکم جا solid تکنیو چی رویا solid تکن بیکو بسران. Solvent particles are also held together by intermolecular forces. Solvent takes particle gani beekwe. Ekawata. These changes occur during the solution formation because energy is required to separate solid molecules and solvent molecules from their neighbors. فما أولين شيء ما بمتوانا ويك أكيدوك تسولفيت. بعد ما نصرف مثلا الشرح كم زور باش تتيجا. I'm going to explain those points on these figures. Let's look at the first figure. Imagine you are dissolving a solid here into the solvent. Imagine it like this. You want to mix, this is like you are preparing to كورغان شاوتان لما اشتغل بفيديو شرحكم بصورهم.
بەڵێ
خلاص
بەڵێ
زۆر باشە. سیرکەن we have like these four fingers and these four fingers. Let's say this one is solute, this one is solvent, and we want to mix them to make a solution like this. But before we mix them, my fingers are not open. So when I want to mix them together, let me just do like this. وجوانت الفيديو كبيرين هساكم. حاول باشتريهم. When you want to mix them like this, first you have to open these four, the solute. All right, you have to open these four. So what do we need in order to break these particles from each other? الفيديو كشنا يعني من جنابنا.
شيء سكرينه ولا ما؟
سكرينه قاعد نعمل بس بوي بحسب فيديو كم بعد. وش شو؟
فيديو خور نكراوتو صار
شلون؟
فيديو خور نكراوتو
نكراوتو فيديو كمان؟
سكراوتو.
سكراوت. كاتب ديال لقد منك خطي بيك واحد.
أنا مثلا فيديو خور نكراوتو بس شير سكرين نبي
فيديو خم نكراوتو؟
ولا بيننا
هاي سيرة. بس
فيديو خوش كردم.
بوي
زۆر خۆش گۆڕی
والله يعني كشي أو من هي
أصلا دينا شر ليكي بدرسك توزع كراية دعاء داخله
بيت أخذ وقعت طول خط السيستم كله سيرة
أنا مش نقول أي خطوة مش كم رجع مصيب بيولوجي وهذا الشرح حقه فيديو خوش كاته شيء
خرزان والله هينك بكاري هنا موبايل كم بحساب بكاري هنا دياري كشي أو من هي زور باشا ما دام ويا منشتيك أكم
تمام صار كراية
كريه وستا
كراية بس وسطها
كاتب أو برنامج يا ما دام ويا كاتب بحطك في الوطن بدرس كتاب شو كان بتاع شرحتهم استكرا وانيا
بلا
زۆر باشە کوڕنا لە کاتێکە باسی ئەو دوانە ئەەکەم کە بتوێنەوە لە ناویەکە ئێمە مانوێمە we have solute like these my four fingers and we have solvents like those four fingers again. So when we want to mix them together, at first we have to open the solute particles. I have to separate the solute particles. I have a leak and Giacomo. Same thing must be occurred for these ones as well. So look at here. At first, when we want to open the solid particles, what do we need? We need energy. كواتا بوي solid particle كان بإلكتريك جابناه فيس ما بتشيا فيس ما بإنرجي كواتا عليها energy أبي absorb ببت كواتو energy absorb كات أما كيا energy absorb دواي أوا أم شو هالبنجيت ليش بابلين كا solvent كه أبي أيش بكريته أيش بكريته بوي بسوان بسنا ويكو تأكلوا إنجا إما we have two things. Breaking bond always needs energy, so it's always absorbing energy. Look at this point here, this point. At first, in the first step, the solid particles must get separated. So if you look at step one, solid particles are getting separated. During this separation, some energy is absorbed. So this is positive. Energy is absorbed. Now, when this is absorbed, solvent particles also must make space. These four fingers cannot enter the solvent unless the solvents also break between them. So for breaking the solvent particles also away from each other, we need to absorb energy, or it needs to absorb energy. So when they absorb, both of them absorb energy, some certain amount of energy is absorbed, both of them together. Let's say this one absorbs 20 kilojoule. This one also absorbs 20 kilojoule. So as a total, we have absorbed what? 40 kilojoules. But bond formation, when something forms a bond, it doesn't need So for this one is also energy is absorbed in step 2. But when the bond is formed, it will release, it doesn't need energy to be absorbed, it will release energy. All right? It will release energy. جاب قرن نصر ده هنا كمان كاميرا كمان no. All right. All right. Now, in the first one, in this point, energy is absorbed. Here, energy is also absorbed. But after the particles, you can add this one. You will say bond breaking, absorb energy, and bond formation, release energy. So if bond breaking absorbs energy, at first we need to bring the solid particles, then solvent particles, they are absorbing. Then when the solute and the solvent get mixed, they don't need energy, they will start to release energy. But this released energy must be compared to the energy absorbed before. Let's say in this example, if the released energy is less than the absorbed energy, let's say how much energy is released. Let's say 30 kilojoules is released. But we have absorbed, the solution has absorbed 40 kilojoules of energy. In the total, when we collect them all together, is more energy released or absorbed? Of course, more energy is absorbed. We call this change here between the initial point where it has started and where it has left. So it has absorbed 20, 20, 40, but it has only given off or released 30 kilojoules from those 40 kilojoules. بيستي وقتوا لو شلاب سيجارانتو كواتب عم شنك زي وقتوا. For example, it has absorbed, in that case, it has absorbed 10 extra kilojoules. It has absorbed 10 extra kilojoules. We call this solution as what? As endothermic. And endothermic solutions are what? Absorb energy. If they absorb energy, it means that they feel cold. So this one, which is endothermic, feels cold. ليش شرية؟ برا. بعم هردو شمان هي. absorb شمان هي release شمان هي. بلام بتوتال شي رؤيات أو بلا مانو enthalpy. This is called the enthalpy. The last part, we have both absorb and release. Some, at first it's absorbed, then it is released. If absorbed is higher than the released amount, that solution becomes endothermic. But if, like this one, released, see, if this is 20, let's say the amount of the release here is 50. So 10 kilojoules has been released more than it has absorbed. كواتا شي كدوا 10 kilojoules زيادة release كدوا وقلوا absorb كدوا. What do we call this solution? As exothermic. And exothermic feels hot. Why? Because it has released some energy. It has produced some energy that it didn't need. At which point energy is actually released? When there is a formation of bond between what? Between the solvent particles and the solid particles. Do you remember that we said if you dissolve anything in water, we call it hydrated? It's hydration. Now, for every other solvent, even if it's not water, what do we call it? Solvated. We call it solvated. What does solvated mean? When a solid particle is surrounded by a solvent. And an example of solvated is hydrated. When a solid particle is surrounded by water, we call it solvated and hydrated. كواتا hydrated نمونية كلا solvated. يعني قد بقى وقت specifically. With water, you can specifically call it hydrated. But if it's not water, you can just, in a general term, you can just name it solvated. So when solid particles are solvated, they release energy. So when they are surrounded by the water, the solvent, the release energy. And if the release energy is more than the absorbed energy, we call that solution as exothermic. Normally, we write exothermic as negative. So delta H here, let's write this down as well. Delta H is the change, is the enthalpy. It is negative. Enthalpy, all right? Enthalpy. How do we find enthalpy? How did we find that? By calculating all the steps. Step 1, which is absorbing. Step 2, which is also absorbing, which is positive, positive, positive. Step 3 is negative. So if we collect all of them together, we collect the energy of the solution. If negative is higher than the positive, we get a total of negative and it will be exothermic. If positive is higher than the negative, then we get an enthalpy of positive, then the solution is endothermic. Back to again. But what do we call this change? We call it enthalpy of solution. Again, if step 1 and 2, what is step 1 and 2? Absorb. What is step 3? Release. If step 1 and 2, absorb, is more than release, the enthalpy of solution, what is enthalpy? Delta H is positive. So in total, energy is absorbed. But if step 1 and 2 is smaller than step 3, step 1 and 2 is positive, absorb. Step 3 is release. So if absorb is higher than release, of course, the total enthalpy of the solution is negative. So it means that generally energy is released. أو كاتب شيء ما بدرجة على energy release بوا. السليرة دوباره سير رسمك كأنه أول نوتي كساوت مع نوتي بينجم سير رسمك كأن. سيرك الليرة release كم ترى لا absorb كواتا ما دام absorb زيادة كواتا دالتا كمان positive درجة endothermic درجة. positive وabsorb endothermic. بلام أجر بيتو دالتا اتش كمان بابنا ريليزا كمان ستيبي سي ليش كاتك ستيبي سي تو بقى عم قصير لبلبه ولا سولفيتد ستيبي سي لم كاتت شيء بانرجي ريليزا عم قصير صار كان هاتبو ايوت لا كاتك كاس سولفيتد بانرجي شيء تو بزهني انرجي ستيبي سي كتشي رويا solid particles are solvated, then it releases energy. You have to know that. If the released energy is higher than the absorbed, then in total energy is released. So هتبقى عن energy release بت. بحشو عليكم. Let's continue. We have two examples. The solution of solids are normally, generally endothermic, except for what? We talked about it NaOH before and KOH. These two with cerium sulfate, Ce2, SO4, sorry, not PO4. SO4 by 3. These are all exothermic. But the others are generally endothermic. So those are for solids. أنا بتشيبون بو solid كامبون. دوباره كمان. بعم dissolution بو solid كان شين توانوي solid كان endothermic كان. بلا بو هنا كان exothermic كان. بلا أوسيانا من هي exothermic كان. أي جاز كان أو بو solid كان زاني ما. أي بو جاز كان. The solution of gases is always exothermic. The solution gas دائما exothermic. بو أنا شرحك لك. Gas molecules are so far apart. In last year in 11th grade, chapter 4, we had 5 assumptions. Gas particles are small and far away from each other, and they don't have attraction forces. So this is depending on those 2 points. Gas molecules are so far apart that there are virtually no intermolecular forces. Like assumption number 4, there are no attraction forces between gas particles. So virtually no intermolecular forces or attraction between them. If there is no attraction, if there is no force between them, and they are so far apart, no energy is needed to be absorbed to separate the solid. اگر گاز كان وين زور ليكو دوربن بيوست كا energy بينه وابزورب كاتو بوي لك بكونو. In the first step, energy was absorbed so that the solid particles are separated. But gas particles are already separated. Gas particles are already far away from each other. They are already broken. They don't have any attraction force. That's why no energy, no absorption is needed. يبقى gas اتوتو بيسي absorb نيا. So the attraction between solute gas and solvent molecules, it's here attraction between كمان there is release energy. يعني attraction كلا بيننا شيء كان release energy. Outweighs means it's more than. It's more than the energy needed to separate solvent molecules. لو زيادة أو energy كرelease بوا زور لو زيادة كبيسي بوا كabsorb بوا أو هيج بو يا كم ينهرنبيس. Look at the figure. We can take this note on this figure. You don't need any energy to be absorbed. So imagine if you remove this part. If you remove this part. If you remove this part, what do you have? You have release only, which is always more than the absorbed here. So look at it as a pillar here. What happens if you remove this pillar? The whole thing will come down and it will be lower. That's why always the energy released is higher than the energy absorbed. شي ما نكر اگر بيتو absorb step يكم لا بريد دائما absorb دوم زور كما لا تشاو يكرليز بو دائما gases are always exothermic. بو gas دائما شيء exothermic. دائما exothermic. باش شباب يجن كيف السيارة هي؟
نعم صح؟
بله.
أظن بس exothermic كتشي بو بس أم بله.
exothermic كتشي كاتك energy زياتر ريزاكريا وقلو absorb به أو بتري exothermic. بون من سيري رسمي دوميان كابيجري دوميان هاجد يقد بي أوي كهاتو تبرو خوارو يعني ريليز بوا. سيري كلا تشاو هردو absorb كها زورترا. لا تشاو هردو absorb كها جورترا. كواتا أول شيء كواتا أول بعام بتوتال شيء ريليز زاترا. بوي أمر جوار solution علين exothermic. والله ما قربنا بو بيوتري اندوثيرميك. والله
تا يعني اگر انرژی که زون رو يشتبو اندوثيرميك اگر زون رو يشتبو ريليز كردبو اكسوثيرميك.
exothermic. تيجي
بس
Any more questions everyone? For next week I will try to put an extra lesson or you can watch the video again. But I think I will record another video, not without you guys, just recording. I'm going to record another video, just a brief summary of enthalpy of solution, because every year some students have problems with this enthalpy of solution. I will explain everything again in more detail in everything, so that you can review the enthalpy of solution again. Because some years there are questions asked in enthalpy of solution. It's an important subject. باشا
ما مصجان عزل نبه
بله
من فكريكم هي قبل توانيت دسك زيادة يعني أواني كيكتوز مشكلة يعني تواني إشتما مدوبارة كي توقر مجال تبت
بس هرشاكي شمان نابه من أوها بلاني أومان هي لقل ما مصاجوني توانا كدسك زيادة دام بهرد بو دابنين بس جاري آليتا كمان نزاني مثلا شون بتامكن شوكا أبي كلاسك نبو درسكين مثلا ناچین بۆ هەرسێ کلاسەکە دەرسی جیاواز دابنین ئەچین مثلا هەرسێ کلاسەکە کۆکەینەوە پێکەوە یەک دەرسی ئیزافیتان بۆ دانێ ئینشاءالله.
ئینشاءالله زۆر باشە بێت چکە لە پۆلی 11 مامۆستا هەر وایە کرد یعنی کلاسی زیایدا دەرسی زیاد ڕشتن بۆ مەکتەب لێوێمان خوێنی